Okay, so let's continue with part 3. We're going now to labs 14 to 18, where we will analyze basic instructions such as add, and, load, and branch if equal, and then the hazard unit. Okay? After that, we'll go to the last lab in this part, which works with the core extend interface. So the goal of this, of labs 14 to 17 is to understand and modify the core. Okay? There is a common structure for all the labs. First, a theoretical explanation, quite detailed, about how each of these instructions flows through the pipeline. Then we perform a detailed simulation in Vivado where these instructions, the theoretical concepts, are examined. And finally, we ask for some exercises to the student where they will analyze the control units, they will analyze related instructions, so for example, other arithmetic instructions, other branch conditional or unconditional instructions, or even include new instructions not available in the ISA implemented in MicroActive. We provide this diagram where the core is, the blocks that compose the core are included. So, for example, the execution data path, which would be included in module M14K, everything starts with M14K, and then EDP for execution data path. This would be the name of the module within the soft core. So the execution data path, the memory management unit, a register file, multiply divide unit. So this is the part that we're going to analyze throughout these labs. There is also a data catch, an instruction catch that we'll analyze in part 4. Okay. And we also provide this diagram which can be useful where the hierarchy of the modules is shown. So the top module is called M14K top. There is a submodule called M14K CPU, then M14K core. Also the iCatch and data catch are included in this module, CPU. And in the core we have the different modules, CDP, which includes some submodules, MPC, which again includes some submodules, and so forth. So we start with lab 14. In this lab we analyze arithmetic instructions, and specifically we analyze the add instruction. So these are the structures in the core that are used by this instruction, by an add instruction. So as I said, we first explain theoretically how the instruction flows along the pipeline. The instruction first accesses the instruction memory, which in this case is made up of instruction catch and main memory. When it obtains the instruction, that instruction is registered for being used in the next stage. This would be the instruction register. Note that the names here, the names of these signals, correspond to the names of the signals in the soft core, obviously. So the student can easily go into the soft core, we'll see some examples later, and find these signals, these registers, which have this name, or these big structures, which are included in these modules, for example. So the instruction would be decoded, the register file would be accessed, and then the two registers are passed to the arithmetic unit, to this other, that computes the addition. As I told you before, MicroActive merges in one stage decoding and execution. This is different to typical processors in Hennessy Patterson or Harris and Harris books. The add instruction does nothing in the M stage or in the A stage. It doesn't have to access memory or to align anything. So it will pass these two stages, and then it will write the result back to the to the register file, right? So that would be the theoretical explanation. And then we perform a simulation where we will show how the instruction executes through the pipeline. So I don't know, can you read these values? Not very well, right?
No, not
so, sorry for that. I'll describe them to you. So we will use this program. This program has an add instruction that adds T4 plus T3 and stores the result in T5. So T4 and T3 are initialized to 2 and 3. So the result would be 5. It would be stored in this register. So in the I stage, here we have the PC for the add instruction, which is 248.0000214. Okay, that's what we can read here. So this is the signal corresponding to the PC. The register file is accessed, and we obtain a 3 and a 2, which are the two values we initialized these two registers. These values are passed to the other, which has this output, which has a 5, okay, addition of 2 and 3. This 5 is passed to the next stage, M stage, to the next stage, A stage, where everything is prepared for writing in the register file during the next cycle. Okay, so you can see here that a register file writing is enabled. Okay, this is the right strobe for the register file, which was 0, and now it's going to be 1 because we want to write in the register file. Here you can see that this signal has changed from 0 to 1. Okay, we're telling the register file that we want to write a new value. This is the register where we want to write dest M. Okay, this is the destination, which is a D. Well, a D because T5 is translated in MIPS architecture to to an index of D. Okay, and we're going to write the value of 5. So in the next cycle, you can see that that register changes from 0 to 5. Okay, so we've written in the register file, we finished this instruction. At the same time, we can see, although they are not highlighted here, but we could see the other instructions in different stages. Okay, so we can easily understand the pipelining of the instructions. Okay, any questions so far? Now, once the student has understood the theoretical concepts and performed the simulation in Vivado, where we ask them to add new signals, to analyze other programs, whatever you want, we ask them to implement several exercises. So we analyze other arithmetic instructions, for example, a subtract instruction, which is another arithmetic instruction, and add immediate, okay, or an SLT, okay. As an example, you can add whatever you want. And we also analyze the control unit for the add instruction. We ask them to analyze specific control signals and how they are generated based on the opcode of the instruction, and so forth. And finally, we ask them to add new instructions to the softcore. And we propose two examples. One is a set if equal instruction, which was obtained from Hennessy-Patterson book. It's one of the exercises that they propose. So we add this instruction to the softcore by changing the control unit and the data path. And also an add immediate assign to PC, this instruction, which is in fact quite useful, as it's an instruction that MIPS added to their latest releases, although it was not included in the release supported in microactive. So your students will be adding a real instruction that MIPS had to add to their processors. Okay? You can tell them they are doing the job of the same job that a hardware engineer in MIPS has done to the processors. Okay? These are just examples. You could add whatever other instruction you want, as far as it's not too difficult. It may turn quite difficult in some cases. Okay? So these are selected because they are medium complexity. So now I'd like to try, as an example, to add this instruction. Okay, in the next slide, we're going to add to the softcore this instruction, which for which will employ obviously an unused code. Okay, if you get the document of the architecture, it's release 3 that is implemented in MicroActive. If you get that document, which is can be obtained in internet or is available in the documentation of the Getting Started guide, you will see that there are some opcodes which are not used. Okay, so we're going to use one of them, this one specifically, for this instruction. And this would be the format. We have a register and an immediate. Okay, these 2 bits should not be used. The instruction must compute the PC plus the immediate shifted 2 positions to the left and sign extended. And this would be the example that we're going to execute. We are adding 4 multiplied by 4 and sign extended to the PC of this instruction and store the result to the register T4. Okay, and this would be the machine code for this instruction. Note that the compiler we are using does not support this mnemonic, obviously, right? So we have to include this instruction in our program in machine code. Is that clear? Okay, let's do it together. I think it's easier. So please open. We'll first use the original bit file, okay, so that you see that nothing works. Why does not it work when we try to execute a program that includes this instruction? Well, when the processor decodes an unused opcode, it will generate an exception. Okay? So one of the tasks that we have to do for including a new instruction using an unused opcode is disabling that exception. Okay? Yeah. So let's try that first thing.
We disable the exception, we add this to the list of acceptable...
Yeah. An exception is triggered when you find unused opcode. So when you find this opcode, the processor will trigger an exception. We disable that triggering. I wanted to show it in Verilog. It will be more clear. Okay, I'll show you in Verilog. Let's first keep the board as it is. If you have downloaded the original processor, keep it like that. If not, download it again, okay, from Lab 1, the one we used in Lab 1. Remember to close all windows of OpenOCD or GDB. And now we're going to load how many Vivado do we have here? Okay, let's.
Bit string is already loaded.
Yeah. So we're going to execute the program in Lab 14, simulation sources add IUPC. Okay, this program. No, it's not running. No. Could you make it run?
Yeah, the bitstream is already running on the board.
I'm not sure because it's not working.
Yeah,
I'll download
maybe
it.
just flash it.
Okay. Yes. So you should see that this light turns on. This is because the processor raises an exception. Okay, this is the code that we see when we have an exception, and that's normal as we are executing an unsupportive instruction. Okay, if we open the program main.c, there we have the new instruction, which is not supported by the original processor. Okay. In fact, we can comment this line. You don't have to do that. Let me do that. And now it works. Okay. It shows 0 because we are not. Now we'll see the program. Now it shows 0, but it's working. Okay, it doesn't raise an exception. We've commented the new instruction. If we now download the modified softcore, that it's available in part 3, lab 14. And with this name, it has at the end add IUPC. Okay, you download that bitstream. If you have commented the new instruction, uncomment it, please. And run again. And you will see a result there, which I'd like you to inspect and see if the result is correct. Okay, 2.1c.
Yeah. You have to program the FPGA. Yeah, program.
So if you open that file, program.this, and you look for the new instruction or for main, or you will find the new instruction placed in PC 8000020C. Okay, if we add this value with 4 times 4, the result is exactly what we are obtaining. Okay, so the instruction looks to be working correctly for this program. Okay. What did we change to the softcore? So in the workshop folder, you have the modified files in the softcore. In this lab 14, you have RTL app, add IUPC. If you go into that folder, you have the core, and you have 4 files. These are the files that have been modified. EDP contains the module for the data path. MPC contains the modules for the main pipeline control, for the control unit of the processor. Okay? This is a top-level module, which just we need to change some instantiations of other modules, but that's it. The main functionality is in EDP and UPC deck. So if we open those files, and this will answer your previous question, if we go to MPC deck, everything is tagged with the name of the new instruction. So if you look for the // space and the name of the instruction, you will find the changes that we have made to the Verilog code. Okay? And here we have commented this line, and we have introduced this new line. This is the signal that when it's 1, it will make the processor to trigger an exception. Okay? So we want to avoid this signal going 1 when we find the opcode for the new instruction. That way, we will avoid an exception triggering when we use the new opcode. Okay? More or less is clear.
I'm surprised that it's not opposite. So you have a list of acceptable opcodes, and what's not in the list is should raise an exception. No, I'm surprised that it's implemented this way.
Yeah, this signal is 1 when there's an illegal opcode.
Yeah,
you could do the other way around.
Easier because I have the case where all the illegal stuff. It's an implementation issue. Seems weird.
And well, we have to change some other signals in the control unit. Obviously, in the exercise, we guide somehow the students where to find things or what they have to do, more or less, so that they can do that. I used some of these labs in a course this year, and most of the students, or some of them, could complete this kind of activities. Okay? I was not very sure if they could finish them without a lot of help, but they could do it on their own after some time. Also, we need to change the data path for computing the addition of PC plus the immediate, right? So if we open this module, EDP, and again we look for the new tag, the tag of the new instruction, we can find that this is the operand for the value that we'll insert in the other. So we're including this. This is the previous line. This is the new line. Okay, we've added this part. Okay, in the control unit we've created this signal, which is 1 when we find the new instruction and 0 otherwise. So this is a multiplexer where we'll only execute this part or follow this path when we have that instruction. And what are we doing here? We are shifting the immediate, right? This is the instruction register. We are shifting it to positions to the left, and we are sign extending it, right? So this is one of the operands, the immediate, and the other one, which is here, this is the previous line, this is the new line. We've added this part. Okay, we've increased the multiplexer, one more input, and we have, in case we have the new instruction, we are using the PC, the virtual address at the E stage. Okay, so we're adding the PC plus the immediate, sign extending. Yes? Any question? Well, you can look on your own at the details or the other exercises proposed. It's very interesting, for example, to understand other instructions. Those are quite interesting. Or to understand the control unit. Well, but there's no time for everything. So let's go on to the next lab, which is about the AND instruction and logic instructions. So mostly everything is similar to the AND instruction, except for the E stage. Okay, the other stages, if we go back to the pipeline for the add instruction, we obviously have to fetch an instruction, we have to decode and execute it, here's the difference, and then a logic instruction does nothing in the M stage, the A stage, and then it writes the result back. So what changes here is the execution stage, where we use the logic unit, which is here. Okay, here's the logic unit of microactive. Note that it can compute AND operations or operations. This would be NAND. Yeah, no, sorry. This would be NOR operation, and this would be XOR operation, right? So those are the four logic instructions that microactive supports. And then, when we obtain the result, we pass it to the next stage, where a multiplexer will select among the result from the addition, from the arithmetic unit, or the result from the logic unit, based on this control signal. Okay? Please go to your slides so that you can see your the simulation values. Everything is very similar to the add instruction, except for the calculation, obviously. Now we are computing the AND, bitwise AND, between 3 and 2, and the result would be 2. Okay? That value is passed to the next stages and then stored in the register file. The program is very similar, we've just changed the add instruction for an AND instruction. Okay? And again, we ask the student for some exercises similar to the previous ones. We ask them to analyze the control unit and to implement new instructions, such as a logic NAND instruction, where they will have to change the control unit, okay? And, they will have to change the logic unit. And another instruction, which again is an instruction that MIPS included in their latest releases of the ISA, and that they will include in microactive, because microactive didn't have these two instructions. Okay. Lab 16, load instruction. The load instruction needs to access structures in the M stage and the A stage. And at the E stage, it has to compute the effective address, as you all know. How do you compute the effective address in a load instruction? Well, you add the value from the register file, register, and the immediate. Okay, immediate sign extended, this is the sign extensor. You add them and you obtain the effective address, which you pass to the next stage. In this lab, we don't go in detail how the data memory is accessed. That's part of part 4. Okay? Here, we just assume that we'll obtain a data from the data memory in one cycle, hopefully. In one cycle, we'll obtain that data. If we hit in the catch, we'll force a hit for this lab. And that data, we will pass it to the A stage, which will align that data in case it's necessary, and will continue to the write back stage. Okay? Note that we've introduced here a new multiplexer which selects among the this value read from the data memory or the value obtained for an arithmetic logic instruction that would be in this signal, would be available in this signal. Okay, again, simulation of a program containing a load instruction. This program, note that we want to, as I said, we want to force a hit, and the easiest way for forcing a hit is doing a load twice to the same position. That way, this load will miss, but this one will hit in the catch. Okay? Because this one will bring the requested value, the requested block, to the catch. Okay? So we'll hit for this load, And here we analyze the flow of the load instruction through the pipeline. As always, fetch stage, we fetch the instruction from the instruction cache. If you look at your slides, you can see that here we have the opcode or the machine code for the load instruction, 8DCD0008 is here. Okay, this is the value read from the instruction cache. It is passed to the instruction register in the E stage, and in that stage the effective address is computed. How are we computing the effective address? T6 plus 8. Okay, here is the content of T6 and here the immediate 8. So we obtain the effective address. We want to access that address in the next cycle. In the next cycle we access that address and we obtain the value D. That's what we read from the data memory. Okay, D. And that value is passed to the A stage, where it's aligned in case it's necessary, and it's prepared to be written to the register file in the next stage. So we want to write a D to the register file, specifically to register D also, because T5 is D. Okay? And in the write back stage, we can see that the register D changes from 0, it was initialized to 0, T5 was initialized to 0, it changes to D. Okay? Any question? Okay, exercises. Analyze the control unit for the load instruction. Add new instructions to the soft core. And again, we add the load PC, which is new in latest MIPS ISA releases. It was not supported in microactive, so an interesting instruction to add. And also an instruction proposed in one exercise of Hennessy-Patterson book, which is load immediate. Okay? We ask the student to implement these two new instructions in their soft core. Finally, lab 17 is about branch and jump instructions. Okay? In this case, we'll analyze separately the E stage of the branch instruction and the pre-I stage of the branch instruction. What was the pre-I stage? We didn't mention it when we talked about the pipeline initially. We said we have 5 stages from A to the write back. The pre-I stage, which is also present in Hennessy-Patterson processor or Harris, just computes the next PC to fetch in the I stage. Okay, this computes the next PC. So the next PC can come from many sources. Here, this is simplified. It can come from PC plus 4, in case we execute sequentially, or it can come from the branch target. And the branch target is computed at the E stage by a branch instruction. Okay? So if we go back and we first analyze the E stage of a branch instruction. What do we have to do for a branch instruction at the E stage? We have to do 2 things if it's conditional branch. We have to evaluate the condition and we have to compute the target address. Okay? The target address is computed as PC plus something. Something which is obtained from the immediate in the instruction, right? So we have to add the PC plus the immediate, and the immediate is multiplied by 4 and sign extended. We obtain the branch target for this branch, which can be used or not, depending on the condition. So the other part evaluates the condition. It compares the 2 registers and it obtains a condition. The branch condition was met or not. If it was met, the branch is taken. If it's not met, the branch is not taken. Different conditions are possible. Branch if equal, branch if not equal, etc. So these values are passed back to the pre-I stage, which we have in this slide. So the branch target and the condition are passed to the pre-I stage. So this branch target may be used as the next PC only when the condition is met. If the condition is met, one, we will use as the next PC to fetch the branch target. Otherwise, we will use the PC plus 4. You see? Yes? And what's in the I stage? Because we have a delay here. Can you tell me what's in the I stage? Here we have the branch. Here we have the target instruction. What's here?
The branch delay slot?
Exactly. Here's the instruction that is in the branch delay slot, right? That will always execute. And this is the next instruction to the delay slot. Yes? And you can see that in the simulation, which I ask you to analyze on your own. Okay? Try to understand the simulation on your own for the branch instruction. There's the program, and there's the result of this simulation. Again, we ask them to analyze related instructions, such as a different conditional branch, or a J instruction, or a jump to subroutine instruction. Analyze the control unit, and include a new branch instruction, which is a branch compact. Again, used by MIPS in their latest releases. This branch does not have a delay slot when the branch is taken. Okay? The delay slot is annulled in case the branch is taken, and it's a new instruction by MIPS not supported in MicroActive. Okay? Let's go on to Lab 18. Lab 18 is about the hazard unit available at MicroActive. Okay? And these are the multiplexers providing the value from later stages in case of dependencies. So the normal path would be to obtain these are the inputs to the arithmetic or logic unit, and these are the values read from the register file. So this would be the normal path. But sometimes, as you know, you have dependencies. So this instruction obtains value and writes it to register T1. This one writes to register T2, and this instruction reads or uses these two registers to compute the value of T3. Okay. Given that we have a pipeline execution, we need to, when this instruction reads these registers, they have not been updated yet by the previous instructions. So we have to forward them from later stages to the execution stage. Right? And they are forwarded through these multiplexers. So this path, or this path, this is the first value, the first operand, and this is the second one. These paths are taken when a dependency or a hazard is detected. So these two signals are one when a hazard is detected between the instruction currently at the E stage and a previous instruction. Okay? And the forwarding can come from two different stages. The next one, or the next to the next. The M stage or the A stage. Okay? And that's determined by this control, by this control signal, by these two control signals. So in this lab, we analyze the forwarding unit. And we do that trying to use the board. So what we're going to do, and this is another interesting activity, we're going to show internal core signals through the LEDs. We'll also analyze a simulation, but we'll also change the soft core to show in the board internal core signals. Okay? Specifically, we will show this signal, this one, and this one. The signals determining the value to select in the multiplexers that select between the register file or the forwarding value. Yes?
Just one question, why isn't there a forwarding path from the write-back stage back to you?
No, there is not. There is a forwarding path from the M stage and from the A stage. At the write back stage, you don't need it as you were thinking.
Okay, okay. But
Right.
when we have when we have a dependency between two consecutive instructions,
Yes.
we can fetch from the memory stage. When we have another instruction in between, we can fetch from the alignment stage. And
Yes.
when we have two instructions in between,
There's no problem because the first instruction will update the register file before the second one
okay.
reads it.
okay, okay.
No problem. Okay. And then we'll be showing in let 0 we'll be showing this signal MPC run, which is not any of these 4 signals. This signal tells us if the pipeline has been stalled or not, because in some cases as we'll see later, we'll have to will not be able to forward the result or just to forward the result, but we'll also have to stall the processor for 1 cycle or even 2. So this will tell us if the pipeline has been installed or not. Then let's 1 to 4, we show the forwarding signals, the signals controlling these 4 multiplexers. And finally, in let 5, we'll show the clock signal. And this, if we keep the clock as originally, this would be impossible to see. So what we'll do is we'll change and we'll change the system and we'll use a slow clock. Okay? So we can observe the signals, the value of the signals at a reasonable speed. So this is the first example. We have dependencies between 2 arithmetic instructions and another arithmetic instruction. Okay? So let me ask you, what would be the values for these signals, for these 4 signals, when this instruction, the add instruction, is at the E stage? So the add instruction is going to add T1 and T2. T1 and T2 are computed by previous instructions which are still in flight, right? So they have to be forwarded. So what would be the values for these 4 signals when the add instruction is at the E stage? Eh? Who's talking? Yeah. Which one? The first one?
No, the one that just forward from the library stage and the one that just forward from the
Yes, and specifically what would be the value in that case?
Well, so I don't know. So, the alignment one is the one.
These 2 multiplexers, will they select the value from the register file or from the forwarding logic? Forwarding logic. So these 2 will have to be 1, right? And these 2, look, this one comes from the A stage, and this one from the M stage. M stage is the next stage. A stage is the next to the M stage. So T2, we have to obtain it from the M stage. Okay, it's the first operand. So from the M stage, this multiplexer would select 0. And T1 must be obtained from the A stage. So in this multiplexer, the A stage also comes through 0. So these 2 signals would be 0, right? As you can see here. And the run signal would be 1. We don't have to stall the pipeline in this case. We just forward the values and continue at the same CPI equal to 1, right? The same. Here you have highlighted the paths that will provide the values to operate with. And here you can see a simulation where you can see that the, again, please open it in your screen. You can see that the instructions, for all the instructions, these signals are always 0. 0 means that we use the values from the register file. That's the normal situation. But then, when the add instruction is at the E stage, which we can identify because the instruction register takes the value of the machine code for this instruction, yes, 0, 1, 4, 9, and so on, which is here. This is the add instruction. Observe that these two signals go high, right? The other two signals stay to a value of 0. This is computed in the control unit. You could also inspect that part. Okay? It's a bit complex, that part. I tried to inspect it. It's a bit complex. Okay. Note that the pipeline is never stalled in this program. Okay. Let's try this exercise. So let's do hands-on. So you try to do it your own and understand it. You can follow the instructions in the document for lab 18. You have a new bit file in lab 18 that you have to download, and you will observe the signals, the internal core signals, through the LEDs. Okay, let's go on. A second exercise that this lab also analyzes is a different hazard. Here you have a hazard between a load instruction and an add instruction. Look, the load instruction will read into register T1, and this register is used by the next instruction. The problem here is different because in the previous case, the previous instructions have already computed the result when this instruction reaches the E stage. But now, the load instruction, when it's at the M stage, it's reading the data cache. So at the same time, we want to use this register for adding with 0 in this case. But that's not possible. So we have to wait till the next cycle. We have to introduce a stall in between these two instructions, right? So in this case, if we try to understand what the value will be for the signals related with the forwarding, when the load instruction is at the M stage, so it's accessing the data memory, and the add instruction is at the E stage, it wants to compute the addition based on the result read, on the value read by the load, the MPC run signal will make the pipeline stall. So it will be 0. Okay, we'll introduce a stall here. Then, when the instruction, the load is at the A stage and the add is still at the E stage because it's being stalled, the forwarding will take place. At that moment, the load has the result and it can forward it to the add instruction. So, in this case, we'll have a 0 value for MPC run when the add instruction is at the E stage and the load instruction is at the M stage, and then we'll forward the value from the load. Why these are the values? Because the second operand is the one we are forwarding, and it comes from the A stage. That's why we select a 0 here. So the path would be from the A stage, where the load is now, we are forwarding a value to the E stage, right? This is what the simulation shows. Look, here you have the same value. This is the instruction register, and you have the same value for 2 consecutive cycles. That's because the pipeline has been stalled. Well, not the whole pipeline. The execution stage and the I stage. The next stages can continue, and that's why the load advances from the M stage to the A stage. But the other stage stays at the E stage. Okay? That's why we observe that the instruction register does not change here. And look at MPC run, which is usually 1 because the pipeline is running, but at this cycle it's 0. That means that the E stage will be stalled. And then in the next cycle, the forwarding takes place. So the MPC B cell res goes to 1. You don't have to take care of this value because the pipeline is stalled, so we don't care about the value that the signals take here. Okay? Well, we go to lab 19 now, which is the last lab in this part, in part 3, and which is about the core extend interface. The goal is to implement your own instructions using the MIPS core extend interface. We've already implemented our own instructions, but this is a different way of doing it. We've changed the soft core itself for implementing instructions. Okay, we implemented the add UPC, but we have to change the data path and the control units. Now we are using the MIPS core extend interface, which allows us to externally include new instructions. Obviously, it's much easier, and if you don't have the soft core, you still can do this, okay? But it's much less flexible. You can only implement specific instructions, okay? Again, we're going to do a theoretical explanation, an example implementation, and then complete several exercises. And I will ask you to complete the final exercise, which is quite nice, I think. It's we're going to implement a floating point unit, add it to microactive through the core extend interface. So the high-level picture of what's core extend interface. You have the microactive core, the microactive CPU. You have a logic unit. This is done based on an example. Okay, we're going to see how we could include a NAND instruction, which is not supported in microactive. Microactive supports OR and NOR and XOR instructions, but not NAND instructions. Obviously, we can perform a NAND operation combining these logical operations, but as an example, we can try to include a NAND instruction. So how do we do it using the core extend interface? Remember that when we did the lab about the logical instructions, we also included a NAND. So that's the way the students can distinguish between both ways of modifying the processor. One way is going to the softcore internals, another one is using this interface. So the register file is provided, the two registers read in one cycle are provided through the core extend interface to outside the CPU, right? So what we would do, we would add a NAND gate outside the CPU that receives the two registers and writes the result back through the core extend interface. That result will be written to the register file. Okay, that's what this interface allows us to do. Okay, we receive the two source operands from the register file, or even from the forwarding path, and we write the result of whatever we want to do here to the core, to the register file. Right? So we can implement here a floating point unit or DSP instructions, very useful for that, for example, or whatever you want. This would be much more low-level detail of the core extend interface, right? Here's the register file, this is the E stage. The two registers are provided to the arithmetic logic unit, to many other places, and also to this module, which is the core extend interface. This module provides the two registers to this module that the user implements. So we're going to implement this module, in this case, with an AND gate for performing an AND operation. So we receive the two registers and we provide the result back to the core. Okay? In the M stage, if we are able to do this operation in one cycle, we won't need to stall the pipeline. The core extend also allows us to stall the pipeline. There's a special signal here called EDP UD stall M. UD is for user-defined instruction, right? That's why the name. So we have EDP UD stall M. When this is 1, we are asking the pipeline to stall. It may be necessary because maybe we're not able to do the operation we want to do in just one cycle. So what we do is we stall the pipeline. We'll do that for implementing the floating point unit because we'll need several cycles for floating point operations. So that's the detail of the interface, right? You have this figure included in the MIPSfpga materials and obviously in the in the whole package of MIPSfpga 2. Let me show you a demo of an AND instruction, or if you want, you can also execute it while I'm doing, okay, and you can see it on your own boards. So the AND instruction will use this mnemonic UD1. This is supported by the assembler, by the compiler, right? So the compiler will understand this opcode, this mnemonic. This is the format. I'm not going into details here of, there are different possible formats for user-defined instructions. This is one of them. We're going to perform some operation between registers T4 and T3, and we're going to store the result in T5. Note that the order is different to usual MIPS instructions. I don't know why. But these are the source registers, this is the destination register. This should be the machine code for this new instruction. So we're going to create a program after modifying the softcore, obviously, that we provide you already modified. We're going to create a program that uses that new instruction, and we'll see if the result is correct. If we're going to initialize these two registers to 2 and 3, and we'll see if we obtain the NAND of these two values through the 7-segment displays, as always. Okay. So let me guide you on the process. We have a new bit file for this lab available in lab 19. So please download that bit file to the board. Lab 19, you have two of them. One is with the floating point unit, the other one is called NAND. It contains the NAND instruction. So download the bit file to the board. You should be able to execute the program, the default program, if you did it right. And now we're going to execute the program using the new user-defined instruction, which if we edit here, the code is included in this folder, simulation sources NAND. If you edit main.c and you look at it, you'll see that it's using the UD1 that we are using for the NAND instruction, right? And now, if we do, as always, load this code, you will see the result on the 7-segment displays. 7 Fs and then a D. We are doing the NAND operation of 2 and 3, and that's correct, right? This is the NAND, this is the result, the correct result. In the workshop contents, you have the Verilog code for this new instruction. Please take a look at it. You have it both in Verilog and VHDL. If you want to take a look at a specific, let me say that all these labs are done both in Verilog and VHDL. This is one lab that we can do in both languages because we don't depend on the core. The core is in Verilog, but outside the core, outside the CPU, we're implementing a program in whatever language we want, right? So take a look to any of the two codes. It's just this file that we implemented outside the CPU, and that, well, it's not so easy to see in 5 minutes. But, well, just let me highlight here that here you can see, well, it supports 2 new instructions, but here you can see the NAND operation. Here's the NAND gate. Here we're defining the NAND gate that we'll use. These are the 2 registers that we'll be using from the core extend interface, and this is the result that we are providing back to the core, right? The interface has some other signals that we cannot go into detail here. So I think that's the important part. So last activity of this part. a very interesting one, I think. Let's see if you like it. I think it's nice. We're going to implement an FPU. Well, we're not going to implement it. It's already implemented. We're providing already implemented, but the idea is that the students can implement it on their own. The lab asks for several tasks. First, you want the students to implement a simple or whatever complexity you want. IEEE 754 single precision FPU supporting FP addition, multiplication, and division. Okay? Using the core extend interface. So we're going to create 3 new user-defined instructions, each one for each of these operations. Then we're going to test it using a simple program. And that's what we'll do today here, because there's no time for doing everything. But the exercise also, and this is not included in the tutorial today, also asks you to implement an algorithm that needs floating point operations, such as a bisection algorithm. I don't know if you're familiar. It's a root finding algorithm that uses floating point, using the new instructions that you've just created and emulating FP operations in software, for which you don't need these floating point instructions, right? And finally, we will compare both algorithm implementations using performance counters, right? And we'll see that obviously the one using the instructions, the floating point instruction, is has a better performance than the one emulating the floating point instructions, right? So today we'll just do these 2 tasks, okay? And we are already providing the soft core with the new 3 instructions that you will use in the simple program computing the floating point operations. Okay, you're going to do this hands-on on your own. You have the instructions in lab 19, but let me recall you. I don't know if you're familiar with the floating point format. Okay, usually processors with an FPU have specific registers for floating point operations, right? Here we don't have those registers. We are going to use the general purpose registers. But we're going to read them or understand them as representing floating point numbers and not integer numbers. So the floating point format in the single precision has this, uses this format. We use the first bit for the sign, the 8 next bits for the exponent, and the 23 final bits for the mantissa, right? And this is the number represented by these 32 bits, okay, in single precision. So when we are initializing these 2 registers to these 2 values, understanding them as floating point numbers, we are initializing them to 4 and to 2 if you apply this format, right? So the instructions that we are adding allow us to add, multiply, or divide these 2 numbers in floating point format, right? Obtaining the result that should be 6 for the addition, 8 for the multiplication, and 2 for the division, right? There is a web page that you can use that allows you to easily convert values from integer to floating point representation. So what I'm asking you to do is to test the new bit file and execute the program included in the materials that does these simple operations, and then you can change these 2 values to any other values that you want and check if the result is correct, right? The Verilog code for the floating point unit is also included in the material, so you can take a look at it if you want later. There's no time now. And obviously the solutions of the package also include everything, okay? So go to lab 19, the instructions. The first part guides you on implementing an AND instruction. Just skip that part and go directly to the FPU part. Lab 19, but the last part, which is FPU unit. Slides for this part are part for the memory system. You can open them and view them in your screen. Now we're going still examining the core internals. The catch controller is part of the core, and many things here are about the catch controller. Also, we'll add an instruction scratch pad in the last lab. This is outside the core, it's in the CPU. But the 5 initial labs are all about catch. So the first one is just an introduction to the catch hierarchy. Then we'll see the catch structure, the catch arrays that make up the catch. Okay, data array, tag array, and way select array. And then we'll delve into the catch controller for 3 labs. Finally, as I said, we're going to implement an instruction scratch pad. So the first one is an introduction we're going to do things similar to what we did in lab 18 for the hazard unit, where we show signals, internal signals through the LEDs. Here we're going to do the same. We're going to modify the soft core for extracting some signals, in this case related with the catch misses, catch accesses, and show them through the LEDs. The soft core modified we already provided to you. You can ask your students to do them themselves. And we're going to test simple programs, executing them on the board. Let me do this as a demo, and then we'll go to have coffee. Well, if you want to do it at the same time, you can do that. This should be available in part 4, lab 20. There is a new bit file called something catch signals.bit. You can download it. Make sure that the switches are all 0, okay? Because again, we're implementing a slow clock, so we have to set all switches to 0, and then we'll change the rightmost switch to 1. But be sure that they are all 0 now. You can program the board. And now we're going to download and execute the program for this lab, which is in part 4 labs, part 4 lab 20. And the name for the code would be execution sources. Let's examine the one called line size, okay? You download the code and you change the rightmost bit switch to 1, and you will observe something like what you see here. So let me show you what signals are we showing through the LEDs. LED 5 is showing the clock signal as before. That's why you see that LED flashing at a rate of 1 second, I think. Then LED 4, LED 3, and LED 2 are all MPC run signals. Remember those signals? Those signals are 1 if the pipeline is executing, 0 if the pipeline is stalled. Let's be a bit more specific. Not the pipeline, not the whole pipeline, but there are specific signals for each stage, or for a pair of stages. So it may happen that these 2 stages, I stage and E stage, are stalled, but these 2 stages, M and W, are not stalled. They are executing. So that may happen, okay? Anyway, for the 3 signals, when they are 1, that stage is executing. When they are 0, that stage is stalled. And finally, we're showing in LED 1 and LED 0 a miss and a hit in the data catch. So when this signal miss goes high, it means that we're experimenting a miss in the data catch. when the other signal goes high, we are experimenting a hit in the data catch. Okay? So the program that we are executing here, you can edit. It's a very simple code, useless code, that we only want to infer the catch line size. Okay, so we're accessing sequentially an array. Note that we are adding 4 bytes, so we are accessing sequential integers, and then we go back again. So we will experiment a miss for every block, and then several hits for the same block. Okay, whenever we're accessing the same block, we're experimenting hits. When we change to a new block, a catch block, we will experiment a miss. And that's exactly what we should observe there. So the question is, can you infer the data catch block size based on the results obtained through the signals? Note that when these signals MPC run are 0, it means that the pipeline is stalled. When they are 1, like now, the pipeline is executing. Okay? So from time to time, these signals go low because we experiment a miss, and then they go high when the block is returned from main memory. And then we experiment several hits, as many as words are included in a block. Yes? One thing you have to know, after we have a miss, we always have a hit for the same data, for the same word. We're doing load words. We have a hit that we shouldn't count. It's part of the previous miss, right? And then we have several hits for the same block. So try to execute that. You're doing already. So this tells us that the block size should be 4 words here. Look, now we have a hit, 2, 3, and 4. And sometime later we'll have miss. The pipeline stalls for several cycles, and then hit, 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 and hit. Right? We have 4 hits, 1 for the miss itself, and 3 more, meaning that the block size is 4 words, as it is in these catches, right? Well, it's a simple lab that allows the student to take a first look at the catch internals. Okay? After this, we're going into much more detail of how the catch controller is implemented, how we handle hits and misses, how we can change the catch size, the catch configuration, and test it on different programs. But I think we can stop now for the coffee break.